Hello everyone, I'm Hyung Wan Do from Professor Karl Berggren's group, and today I'll be giving a presentation on three-dimensional nanofabrication using HSQ PMMA bilayer resists. This work was supported by Taiwan Semiconductor Manufacturing Company, TSMC, and National Science Foundation. So why is 3D nanofabrication important? 3D devices are difficult to fabricate, but they offer unique advantages over planar devices for many applications. There has been a growing interest in 3D devices such as photonic crystals, metamaterials, nanoelectromechanical systems, NEMS, or nanofluidic devices. We can see two examples below. In the first image on the left, we can see 3D spiral photonic crystal. This was fabricated using direct laser writing. On the right, we can see 3D vertical NAND flash memory, which was fabricated using standard lithography. However, methods for generating such 3D devices are generally slow and expensive. Therefore, we need to develop a new fabrication technique to build complex 3D nanostructures. So many researchers have worked on using electron beam lithography to fabricate three-dimensional nanostructures. The first method, which is the most commonly used, is using consecutive overlay exposures. In this method, each layer is exposed in a separate lithography step. After the first layer is exposed and developed, a new layer of resist is spin-coated on top. Then, a new pattern is aligned with the previously exposed pattern and exposed and developed. This process is repeated multiple times to achieve multi-level structures. Here, we can see three-level structure fabricated from three separate exposure processes. The second method is to use low and high electron energy exposures. Here, the electron energy is used to control the depth of electron exposure, and therefore the depth of the structure that is exposed. High energy electrons are used to expose deeper patterns, and low energy electrons are used to pattern shallow structures. Here we can see 5 freestanding bridges, which was patterned using low electron energy exposures, and the two anchors at the end of the bridges, which was exposed using high electron energy exposures. The third method is to use grayscale lithography. In this method, a low contrast resist such as PMMA is used to control the development depth using electron dose. Here we can see staircase profiles that was fabricated using this approach. The three previous approaches used a single layer of resist for each exposure. However, another method is to use a bilayer resist stack. In this method, the top layer, which is usually hydrogen silsesquioxane or HSQ, is patterned using electron beam lithography. And the bottom layer, which is usually PMMA, polymethyl methacrylate, is undercut using reactive ion etching or oxygen plasma. Here we can see undercut structures fabricated using this approach, and these kind of structures are used for liftoff. However, these approaches have some problems. For the first two methods, consecutive overlay exposures and low and high electron energy exposures, we need to have alignment marker and accurate alignment routines for each additional layer. For the third method, grayscale lithography, the feature size is limited to several hundred nanometers, which is generally too big compared to the other methods. And finally, for the bilayer resist stack method, the final structure is limited to certain shapes because all structures must be derived from only undercut structures. To avoid these problems, we developed a new process for fabricating complex 3D nanostructures. Our goal was to develop a process that is simple, rapid, and self-aligned so that we don't have to use alignment routine in the intermediate process. So we developed two different processes using the sensitivity difference between HSQ and PMMA. The first process is the single dot exposure process. First, the bilayer resist stack was prepared by spin coating HSQ and PMMA on top of a silicon substrate. We first spin coated PMMA on top of silicon and baked the film in hot plate at 200 degrees C for 2 minutes. This hardened the film so that HSQ could be spin coated on top of the PMMA. A bilayer resist stack was formed without resist intermixing. Next, we exposed the dot array with the dose necessary to achieve negative tone PMMA. Because HSQ has a higher dose sensitivity to electron beam than negative tone PMMA, a larger diameter disk was formed in HSQ on top of a smaller diameter PMMA post. After exposure, we developed the sample in 3 steps. First, the unexposed HSQ layer was removed using salty developer consisting of 4% sodium chloride and 1% sodium hydroxide. Next, the lightly exposed PMMA layer was removed using MIBK and IPA. Finally, the unexposed PMMA was removed using acetone sonication. The final structure is a mushroom-shaped post. This SEM image shows the result from the single dot exposure process. From the collapsed structures, we can see 2 separate layers. So the PMMA post, which appears as a darker layer, is indicated here by the arrow. And the HSQ disk, which appears as a brighter layer, is shown here. However, the collapse of the nanostructures was a problem. We developed a simple method to avoid collapse. So in the previous step, we removed the unexposed PMMA layer using acetone sonication. We removed the sonication step and just developed the sample in acetone. Next, after development, we rinsed the sample with low surface tension solvent, IPA, to prevent collapse. This SEM image shows the same structure, but using a higher exposure dose. Compared to the previous image, about 6 times the electron dose was used. We can see that the diameter of both PMMA post and HSQ disk was increased. However, it was difficult to get a clean structure because we were using such a high dose that the HSQ structure was defined by backscattered electrons rather than primary beam. Therefore, we had to develop a new process to prevent this edge roughness. And on the top right corner, we can see 2 collapsed structures. And finally, when we place the posts close to each other, the top HSQ disks cross-link to each other and form the wavy line. So in here, we can see freestanding bridges, wavy bridges, that is supported by PMMA posts. However, we wanted to get a smooth, straight line instead of a wavy bridge. So we developed a new process to solve this problem. The second process we developed is the double area exposure process. So first, we prepared the bilayer resist stack using the same method used in the single dot exposure process. So HSQ was spin-coated on top of PMMA, which was spin-coated on top of a silicon substrate. Next, instead of using a dot exposure, we used an area exposure to expose circles to make posts. Because we are not using dot exposure, we could control the size of the posts using the pattern we input to the equipment. Therefore, we used the minimum dose required to achieve negative tone PMMA to minimize the overhang structure or the overdose of HSQ. Therefore, we achieved about 10 nanometer increase in diameter in HSQ structure compared to the PMMA structure. After exposing the PMMA layer, we exposed the HSQ layer using low dose exposure. In here, we exposed 2 lines on top of the PMMA posts. This way, the region under the HSQ lines were only lightly exposed so that they could be removed using MIBK and IPA in the development process. And after developing using the salty developer, MIBK and IPA, and acetone, we could get a freestanding bridge or any type of structure as long as the top HSQ layer covers the bottom PMMA layer. In here, the same type of mushroom-shaped posts was fabricated using the double area exposure process. Compared to the single dot exposure process, we could accurately control the dimension of each layer. So in here, we can see 60 nanometer diameter HSQ disks on top of 30 nanometer diameter PMMA posts. This type of accuracy would not be achievable using the single dot exposure process because in the single dot exposure process, both layers are exposed using the same dose so that the 2 diameters are related to each other and they cannot be independent. However, using the double area exposure process, we could have more freedom in the dimensions. So we could control each layer more with more degree of freedom. This SEM image shows a tilted view. We can see that the HSQ disks are actually floating on top of the PMMA posts and not touching the silicon substrate. We can also fabricate freestanding bridges using the double area exposure process. In the single dot exposure process, we had the problem of the waviness. However, we avoided that by actually drawing the line instead of cross-linking two disks. Therefore, we can get a straight line and we can control the width of the line or the diameter of the posts. This image shows a tilted view of the structure. So in here, we can actually see that the bridge structure is actually freestanding and the area under the bridge is empty. Finally, we could fabricate a more complex structure such as a freestanding cross grid supported by PMMA posts. So in this image, we fabricated freestanding cross grid supported by PMMA posts. We fabricated 75 nanometer HSQ grid on top of 50 nanometer diameter PMMA posts. This image shows a tilted view, and we can actually see that the grid is freestanding and supported by PMMA posts. And the structures we can fabricate are not limited to just posts, grids, or lines. We can fabricate any type of structure as long as the top HSQ pattern covers the bottom PMMA layer. So now I'll compare the two processes, the single dot exposure process and the double area exposure process. In the single dot exposure process, the possible structures were limited to mushroom-shaped posts and wavy lines formed from merged posts. We could not fabricate grids or any other type of structures because we were using dot exposure to make all the structures. However, in the double area exposure process, we could fabricate different type of structures and control the size and shape of the nanostructures with more degree of freedom. Therefore, the double area exposure process is more preferable compared to the single dot exposure process. Next, we used the double area exposure process to fabricate topographical templates for block-o-polymer self-assembly. So the first two images show previous work from Amir Tavakoli, who is a postdoc in our group. So on the left, we can see block-o-polymer cylinders forming mesh-shaped structures, which was controlled by a 2D array of HSQ posts. And the second image shows a tilted view, showing that the top block-o-polymer cylinders are aligned from left to right, and the bottom block-o-polymer cylinders are aligned from top to bottom. So these two images show that we could already fabricate complex 3D block-o-polymer patterns using 2D array of templates. So the idea here is that if we have one more degree of freedom in the vertical direction and fabricate three-dimensional templates, maybe we can get a more complex morphology that's useful. So the final image shows mushroom-shaped posts fabricated from the double area exposure process used to template the self-assembly of block-o-polymer cylinders. However, this is not very interesting because the block-o-polymer cylinders are aligned in the same direction. We are currently working on ways to solve this problem. So in conclusion, we developed two different processes to achieve self-aligned 3D nanostructures, the single dot exposure process and the double area exposure process. Next, we believe that our approach can be extended to a multi-layer resist stack with different resist combinations. So we believe that we can use different resists as long as the resist can form a bilayer without resist intermixing. And also, we hope that we can make a multi-layer resist stack, which will allow more complex patterns to be generated. We have tried PMMA in anisole and PMMA in chlorobenzene, but we have not succeeded in making a multi-layer resist stack. We will work on this in the future. Finally, feature sizes might be further tuned by varying the development process from layer to layer. By changing the developer or the developing temperature or the developing time, we believe that each layer can be more finely tuned and different feature sizes can be generated from layer to layer. I would like to end my presentation by thanking the funding source, TSMC and NSF, and the people who helped me with the research. Thank you for listening, and for more information, feel free to contact me. And we recently submitted a paper, 3-dimensional nanofabrication using HSQ PMMA bilayer resists. So feel free to take a look. Thank you very much.